So, hello everyone. Welcome to the TIFR Colloquium. I would like to introduce Professor Kaj Nyström from Uppsala University, and he'll be telling us about parabolic operators, fractional powers, weights, and the Kato square root problem. Over to you.
Okay, thank you very much for the invitation and the introduction. It's a pleasure to get this chance to talk to you. And as I mentioned, Agni Bilinear had invited me a couple of times to come to your institute, but for practical reasons so far I haven't been there. But I hope I will be able to come in person in the not too distant future. So what I will talk about parabolic operators, a topic that has been quite dear to me for quite some time. This sort of is a subset of project, number of people involved, they will be mentioned. And sort of a nice blend, I think, about parabolic PDEs, sort of functional calculus, operator theory, if you prefer stochastic processes, and boundary value problems. It all sort of interlinks when you start to look at things in this quite general sense I will be discussing. So let's go to the first slide. So these are the operators we are working with. So sort of far-reaching generalization of the heat operator. So if this W was 1 and A was the identity matrix, you would have the heat operator. So in this case, you see the W here is, it will be what you call a weight. And then you have this matrix A, which is depending both on position and time. And in this context, we work with complex coefficients. So the complexity of the coefficients, we have some uniform boundedness from above. So if the weight was 1, you would have sort of but the uniformly bounded operators. You would say the coefficients are uniformly bounded by this C2. And then you have an ellipticity condition, which is a condition now on the real part of the eigenvalue for this matrix is supposed to be bounded from below with a constant C1. So if you ignore the weight, this is what you would call bounded and uniform elliptic operators, parabolic such with complex valued coefficients. And then there is this weight in here, as you noticed from my talk, and this weight is sort of assumed to be in this talk. You see the relevance of that, it's what is called an A2 weight. What is important to note that this weight here is not depending on time, it's just space dependent. And in general, I mean, it's a completely open problem how to study in several respects parabolic operators where you potentially assume the weight to depend on time, for the obvious reason that it's unclear here even how you should define weak solutions, because basically you would have this weight in front of here and you want to move the time derivative will hit the weight. So it's unclear unless you start to make some regularity assumption on the weight, how to even formulate such equations. So you might ask yourself, why look at such general operators? And the weight, as you will see, will be important. But in general, the case is suppose they're just interested in the real case. And suppose you're just interested in boundary value problem for operators with real coefficients, but for example, with the coefficients not being symmetric. Note here that no assumption of symmetry here, right? But quite often, if you look at elliptic operator, you might assume that the matrix is symmetric. It's relevant if you do partial integration and this kind of stuff. But if you want to study sort of certain boundary value problems with non-symmetric coefficients and beyond the case of constant coefficients, you tend to have to go up into a complex context to even handle those real valued cases. So that's one reason actually to study complex coefficients, that you even need it seems, with technology you have to study certain problems with real coefficients when you assume, for example, that the matrix is non-symmetric. So what is sort of the outline and motivation for the headline? I think is about on the other side of this bar, but what this is saying this slide is saying outlines, summary, and yeah, what else? Conclusions, perhaps. What I've been interested in is to look at one thing, look at fractional powers of these operators in this generality. So you take this operator had, and note now that what I'm saying here, in this case, the weight is equal to 1, and you take a fractional power between 0 and 1, the S, and you might wonder, I mean, first of all, I mean, how to make sense of such an operator in this generality and so forth. And then you might be interested to see if you can localize this operator. You probably, if you know anything about this field, you know that there is what is called some localization techniques for these fractional operators, at least if you just have the Laplacian, which leads to sort of a standard second order PDE problem when you add one direction, in this case the lambda, and you see here you get something which you might consider as a PDE there, where you have the operator and then you have one more direction, and the price you pay is that you have this weight now. So that will be an example of a weight in this space where you add one direction, the lambda direction. So you might look at problem of the following nature, that you start with your function u, you try to solve this problem, and as we will see, it will be relevant that you can do this in such a way that this sort of generalized Dirichlet to Neumann map is equal to the this fractional power of this operator. So this is in some sense a way of you sort of localize the operator, the fractional operator, by looking at an extension problem, and then you enter into the context of weighted operators instead. So of course you can look at weighted operators for many reasons, but it's one motivation. And if you go into these kind of weighted operators, you might be interested in then study boundary value problems for these operators in general. And then based on what I said before, you somehow have to go for rather heavy machinery if you're going to study boundary value problems in, say, LP for just real coefficients, but non-symmetric such. And the only approach there is at this point to those problems in the sense I discuss here, which is not properly defined. I'm talking about the Dirichlet problem for this operator in the upper half space, where you have data in LP and you want some regularity up to the boundary, usually controlled in something what is called the non-tangential maximum functions. That's equivalent to saying that the parabolic measure, which is the corresponding measure, the measure corresponding to the harmonic measure in case of Laplacian, that this parabolic measure is mutually absolutely continuous and have sort of certain quantitative estimate with respect to surface measure. If you look at those kind of boundary value problems, which are the relevant one in the LP context, the only approach to those problems at this time is actually to go into the complex setting, prove certain square function estimates, and in particular prove what is called the Kato square root problem. So if you look at weighted operators, which sort of tend to appear, for example, in this context, it becomes relevant to try to prove a Kato square root estimate for these weighted operators. And this is such an estimate. That means that you should somehow be able to make sense of the square root of this, this parabolic operator. And if you look at then the square root of that, it's L2 norm. Now in the weighted space, you should be able to estimate that with some kind of energy which resembles the energy you get if you take the square root of the heat operator. And if you do this, the square root of the heat operator on the Fourier transform side, this is exactly what you get. So in the case when this is a stationary operator, so you ignore this guy and you ignore the t here. This was a famous problem, the so-called Kato square root problem for, in that case, unweighted elliptic operators that was solved about 20 years ago now by Pascal Lecher and Steve Hoffman, Michael Lacey, and Alan McIntosh. And it's sort of a hard PD function analysis operator theory result, but it has turned out that it has a lot of applications to study very concrete boundary value problems for real operators, assuming a lack of symmetry and so forth. So what we have been working is to do similar things in the parabolic case. One thing Pascal and myself and Morsegic, we did this in the unweighted case a few years ago, and also what I might mention at the end, corresponding result in the weighted case. So what I would like to, somehow this was the summary, then we're going through the talk, is that the parabolic domain is much less developed than the elliptic one, of course. And there is a lot of intriguing and interesting problems related to operator theory, boundary value problems, and also branches into some interesting new stochastic processes, at least new to me, I should say, if you in particular study these fractional operators. So if nothing else, hopefully some people, perhaps younger, get slightly inspired by the many fields these problem branches into, and that you get inspired to do more and do better. That's what I might hope for. So let us go back to the situation perhaps some of you are slightly familiar with, is that of the fractional Laplacian, which is behind the bar up there. So the fractional Laplacian is basically you take minus the Laplacian to fractional power. You can define it many ways for your transform side. But of course, it's a fundamental object in potential theory. There is this book of Landkoff, which I read when I was young, in potential theory, which is, you can read a lot about the potential theory related to the fractional Laplacian. Fundamental in the potential theory, single integrals, harmonic analysis, and also to the context of stochastic processes, what is called Levy or stable processes. What was somehow an interesting development a few years ago was what is called now the Caffarelli-Silvestri extension trick, namely that if you look at the a function, in this case u, and then you solve this boundary value problem. So again, you go up in one space dimension, you add a lambda. And then you look at, again, this, you take the Neumann derivative or normal derivative to the boundary of the direction you add. And then you have this factor and go to the limit. So this is what we call a generalized Dirichlet-Neumann map. Then you actually cover the fractional Laplacian acting on u. So let us see here that in the case when s is equal to 1/2, then you see this weight, then it collapses into just the identity. So what you then have is just that you have the Laplacian in the upper half space, and you have boundary data. So just solving the Laplacian upper half space, you can write out the fundamental solutions and so forth. And in that case, of course, this becomes what you then would call the true Dirichlet-Neumann map. And if you look at the s equal to 1/2, this is of course a special case for the obvious reason. I mean that if you have s equal to 1/2, you can just do the extension by basically taking e to the lambda, and then you take the square root of the Laplacian upstairs. So look at that operator, which has, well, all the properties you would like to have. And then if you just look at the function and you differentiate twice through, you get that it will be solution to this equation upstairs. So of course the s equal to 1/2 is a special case, right? Because it connects very well to this second order structure. So somehow most of the stuff I will discuss is more intricate if s is different from 1/2. The interesting thing with this is that, of course, if you do this extension trick and then you look at some domain down here and assume that the fractional Laplacian is 0 there, that will then show that this generalized Dirichlet-Neumann map is 0 on this domain. The idea is then that you can do an even extension over this domain. Basically, you have omega, right? And then you make it into a cylinder by adding the lambda direction. And first you have information in above omega, but then you can do an even extension of the function over this boundary lambda equals 0. So you get it in all of this cylinder. So the domain is sort of removed. So that means that you can study properties of solutions to this equation equal to zero domain by actually looking at corresponding solutions to this localized problem. And that is what you then somehow gain. You localize your operator, and you can, for example, prove Harnack inequality easy by just using the Harnack inequality for these degenerate elliptic equations. And all those estimates, you should note now, which I haven't said, that this guy now, lambda to 1 minus 2s, it's an A2 weight in this context. You can do the calculation, I defined A2 weight. So this is an example of an operator with a weight which is A2. And those operators were studied in much more generality by Carlos Koenig, Jim Fabes, and David Garrison and Raul Sarpione in the 80s in a sequence of fine and well-written papers, where they develop a lot of what is usually considered relevant boundary estimates and so forth. So if you do this localization and have this, then you can use those results to make conclusions. So what is interesting is that you enter into the context that we people, at least me, I like, analysis on domains, but you also lose something, because when it comes to certain boundary estimates for this equation then in domain, if you localize, then it turns out, of course, that the geometry of the boundary omega enters into a parameter. But if you look at it from a probabilistic perspective, and you then think about solutions are described by such a Levy process, and the Levy process makes discrete jumps in contrast to Brownian motion. So from that perspective, the Levy process doesn't really see the boundary in the same way as the Brownian motion does. So from a probabilistic perspective, the boundary is of lower order when you study these problems. So while if you want to prove certain boundary estimates for this equation or non-negative solution in a domain, if you do analysis, you usually end up in Lipschitz or NTA and this kind of stuff. But if you look at what the probabilistic people do, they can prove it in any open set. So what I'm saying is, if you localize, of course you gain something, right? You get back into a situation where everything is local, and you at least you're more used to think of it. I am more used to think about it. But on the other hand, you lose something in the sense that you have to start to impose restriction on the domain omega and so forth, which you do not necessarily have to do if you do it from a probabilistic perspective. So if you were competent enough, of course, the best thing would be to be a master both on analysis and probability, right? Stochastic processes. But usually we tend to work in both fields. But it's really worth reading up in the stochastic or probabilistic literature on these problems, and not necessarily only read the analysis part. Yeah, so I just want to emphasize, I mean, there has been a lot of action in this field where you can start to look at this problem in the upper half space for a much more general operator, say a sectorial operator on a Banach space. So what is sectorial operator? It's just an operator basically which has spectrum in a sector making an angle with the positive real axis in the complex plane. And the smaller angle, usually the better properties you have of the semi-group E to the lambda A. So of course you can pose the question, if I have such a sectorial operator and some function space, can I sort of make sense of this then function space value of the E, where you start with some function, right? You solve a problem in the upper half space involving this operator A, and assuming that what you start with is in the domain of the operator AS, can you then conclude that you have this sort of relation between a Dirichlet-Neumann map and the fractional power of this operator? So there are many problems here, of course. I mean, existence uniqueness for this problem upper half space, properties of the Dirichlet-Neumann map, and its relation to these fractional powers. And of course, as I said, it's more or less difficult depending on the properties and information you have about A. But there is a substantial literature in this more general operator theoretical setting. The first setting was more PD, right? The fractional Laplacian. But you can look at more abstractly from the perspective of operator theory also, and that set of people usually don't look at the PDE questions, but then they are interested in this sort of if you can localize the fractional power of this operator. Yes. So what about parabolics then? I mean, if you would like to look at fractional parabolic operators, you have many options, right? One is that you take say the fractional Laplacian, and you add the time derivative. Then these, if you know anything about finance, there is this already in the 60s, Mandelbrot he was observing the prices of cotton, that the price movements in cotton, they were much more likely to have large price moves than sort of the standard normal distributed random value would anticipate. So he discovered that returns on assets quite often have fat tails, right? And so ever since, there's been a lot of approaches trying to sort of set down more refined stochastic processes in finance, trying to capture these fat tails and making more realistic models of how actual asset moves. And one approach is, of course, that you, instead of you Brownian motion, you take let your asset be driven by a Levy or stable process. If you do that and price option in that model, the options will solve either the kosher problem or an obstacle problem, depending on the character of your option, involving these, if you might call that, fractional parabolic operators. So they are, of course, very much motivated, right, from that perspective, and they are used on a daily basis out there in trading and so forth. Another is, of course, that you either keep the Laplacian, you take the fractional, and you add a fractional time derivative. Turns out that these processes, these PDEs, if you might call them, they occur also in the stochastic context where you have a stochastic processes with memory, so that your the history of your path sort of is tend to influence what's happening today, and that we all agree is relevant, is structurally relevant in finance also. So then you might wonder, I mean, there are all different other options. One is to take, if you now take the powers of the heat operator, right? You can do that from a math perspective, as we will discuss. You might think, well, is there some related things in the stochastic world? And then it turns out that there is actually a substantial literature related to these operators, closely connected to what is called continuous time random walks, which I will, I think, briefly describe in an upcoming slide. But in this case, the thing is that the jumps, the process do in space is coupled to certain random waiting times. So the particle is stuck at some point, then after a certain waiting time, it will jump, and how far it will jump will be dependent on this waiting time. So this is in the literature called anomalous diffusions, and I don't know if that term is well defined, but it's tend to mean, you could tend to say that it's at least when both time and space are coupled in such a random process, you would say that it is anomalous. And in the physics literature, there's quite a lot written on this, but much less in the math community. So I just want to emphasize that the key difference here between this operator and its associated processes, and this is, of course, that in this case, both time and space are coupled, which is not the case here. So, of course, from that perspective, from an analysis perspective, these operators might have advantages compared to this. But as we'll see, and that's the reason I become interested in this guy has also analytic advantages, which actually these do not have, depending on what perspective you consider. So what I'm saying, this wrote actually quite a lot of interesting work going on in this context. So even if you're interested in analysis, I think it's worthwhile really going into looking at what the people in probability are doing here from a number of reasons. So let us look a little more at this operator, the fractional heat operator. So how is it defined? It's defined on the Fourier transform side, as you expect. You take the multiplier associated to the heat operator, you take its power to power s. You can manipulate that and write it down as an integral equation. You can write it out actually as stated. where the fractional heat operator acting on U at xt is you have get the differential quotient here, or actually difference, I should say, where you see you have xt fixed, and then the position and the tau is varying, and then you weight these differences with the kernel like this. And the kernel is upstairs. You have the heat kernel in n dimensions. So that means that this is position, and this is what you should call standard deviation. And of course, this kernel now just is supported when tau is positive, as we know the heat kernel is. And then you also have an additional component coming from that basically the weighting times will be distributed according to a Levy process with a sort of a tail weight grid described by this S. And then you have a normalization, making this into a probability distribution. So the fractional heat operator is no more, no less stated, and it's interesting, rather elementary calculation based on this normalization gave that, as you hope, right, when S go to 1, you get the heat operator. So this is the way you can define it. And let me just here briefly discuss again, because I sort of tend to like, and for me it's just a sort of a new angle. I think it will be really interesting to get further into this if you're in analysis that it concerns these underlying processes. And as I said, in this case, you should think about a particle which is moving at the discrete points in time, and in between is just sitting there waiting. So you get some sum of the jumps up to the nth jump. That is sort of the time point when the nth jumps occur. And when a jump occurs, you are moving a random variable yi. So that is, if you start at 0 at the position at the time of a jump, the particle jumps sort of either up or down if you're in 1D, or other one it jumps to some position in Rn, say. And then you look basically at the position of the particle up to time t in the natural way. So you basically is just summing up to t the could occur a random number of jumps, right? Jump times, and at those jump times you're jumping this yi. This is in the literature then called the continuous time random walk. And if you, again, since I used to be, actually I worked out in the financial industry, I always sort of think about it in financial terms. So what is this? This is actually what you might call a loss process in credit risk. It also quite often referred to a queue process, renewal process, and this kind of stuff. But in this world, here is defined as a continuous time random walks. So let me just emphasize one thing if you know Brownian motion, there's something which is called the rescaling limit. When you start with a random walk, and then you construct Brownian motion as a scaling limit, there is very interesting literature on doing similar thing in this context. And if you now assume that the random times are distributed basically with the Levy one-dimensional Levy process with tail index S, and whenever you make a jump, your jump is conditioned on the waiting time as stated, then it turns out this is incomprehensible because I'm leaving out a lot of details. But then you can actually study scaling limits of these two, the jump time process and the position time. And in the scaling limit, you will actually get something of a stochastic process, which has a particular Levy measure describing how it moves. You know, in the case of Brownian motion, we know that Brownian motion, how that moves, it's given by the Gaussian, right? So in this case, the Levy measure becomes this. As you can see, this is exactly the kernel we had on the previous slide. So that is the connection between this. You can look again, these are operators either from a Fourier transform perspective as a singular integral, or you can look at from the perspective of stochastic processes. So what is my take on this? Why did I become interested in? Well, it's basically this thing, right? I was thinking I was talking to some people, what is really the parabolic counterpart of this Caffarelli-Silvestri extension trick? And then together with one of my students, at one point I started to go into this, and what we discovered sort of that if you take the fractional powers of the heat operator, you can localize that exactly like Caffarelli and Silvestri did. So we proved this in a rather short, but I thought interesting paper anyway, that suppose you take a function, you solve this problem, I claim you can do that, and then you look at this Dirichlet-Neumann map, actually you will get the fractional heat operator. So this operator now, the fractional heat, it has the potential advantage then that you can localize it. So if you want to do something along those lines, this is sort of the correct operator. To my knowledge, there is no localization trick available if you look at the other parabolic operators I mentioned on the previous slide. But for this guy, you have a localization, and you also have a connection to a rather involved stochastic processes. So in my opinion, this is a very interesting operator to study. So what you then can do is you can do the same trick, it turns out, meaning that you flip evenly, if this is 0 on some now space-time domain, you flip it over the boundary, this new introduced lambda boundary, in an even way, and you will get the solution to this equation over this boundary with, of course, now the lambda will not be lambda, but will be absolute value lambda. And let me emphasize again that, again, this lambda is an A2 weight. So that's sort of my the reason I started to look at this, because it is it's a favorable operator if you would like to do a parabolic version of Caffarelli-Silvestri extension trick. And let me emphasize, if now you take away everything which is T related here, you get exactly what double Louise did prove. So how do you do? The question is how then, if you have, how do you do the extension, right? If you have a function, can you construct such an extension? And in this case, it turns out, you know, that you can write this down rather explicitly, and we'll throw some formulas at you. We don't have to go through it thoroughly, but the point is to highlight and think that if you introduce this operator p tau, which is an integration of the function u against the heat kernel as stated, what this really is that you add a parameter, in this case called tau, and if you look at this as for positive tau, when tau is 0, you see, then what do you have here? Then you have that the heat kernel at 0. So what this will be is that you integrate the Dirac delta against this guy uwt, the Dirac delta at x. So this will actually, when tau is 0, this will be equal to u of xt. And then as tau goes up, it will have the properties of a semigroup. And if you don't know what a semigroup is, it is sort of satisfies number of properties. In particular, if you take the composition of p tau 1 with p tau 2, that will be the same as to go take p of t tau 1 plus tau 2 immediately. And there will be a few other things. The important thing is that it actually turns out to be a semigroup. Using that semigroup, you can actually rewrite the formula I had previously on the slide in this more complicated way. So it's well known that you usually can express the fractional powers of using an underlying semigroup. And in this case, you can do it explicitly like this. And then it turns out that you can define the extension of little u to big U in the following way. You take this semigroup acting on u and tau, and then you do some integration here, and you have this parameter lambda in here. It turns out that this guy actually will solve this PD I had on the previous slide. And if you then look at the Dirichlet-Neumann map, you will recover HS. So what this is to say that in the case of the fractional heat operator, you can write down the extension explicitly. And it somehow, the key thing here is that you're using a certain constructed semi-group in the construction of your extension. Yeah, so this is, so now I've been interested to look at these things where you have this much more general operator with potentially complex coefficients, right? So this is what I've been working on with one of my students, Malte Litsgård. So what we do then is we look at these operators, start with complex bounded measurable coefficients. We're interested to make sense of this operator H now. I mean, it's far from clear, right? Because, yeah, how do you even make sense of these powers? And what we're able to do that, and then we studied these operators HA's relation to this sort of boundary value problem, if you might call it, which is a localized one. How? But I mean, now it has to be formulated in an appropriate way, as you will see. And what we then did was that if you now start to assume that the coefficients are real, we use these results actually to derive local properties, or not necessarily local properties, but regularity properties of solutions to this equation equal to 0 in some domain. And note now, and the operator is non-local. If you have your domain here, this is in space and this is in time. Since it's non-local, the right way of formulating a Dirichlet problem is that you look at the equation in the domain, and outside of the complement of the domain, so to speak, you have to have your data. So the data has to be globally imposed outside the domain. So sort of a consequence of our work is at least that we allow for non-symmetric and time-dependent coefficients. And as I said, if you start to look at sort of more straightforward generalization of the heat operator, so you take time-independent real symmetric coefficients, well, then basically you can do what I had on the previous slides using the fundamental solution for this operator. And in general, much more tools are available, like spectral theory and so forth. So what we had tried to do here was to look at this very general situation where you allow for all of this. But of course, then we cannot do Fourier analysis and sort of spectral methods in the more traditional sense. So you have to do something else, right? So let me describe slightly about that. So the first is, how do you look upon this operator H, right? What is it? Far from clear, right, how to define HS in this generality. Okay, so the way we do it is that we look at it from a more abstract perspective, and namely as an operator defined by a sesquilinear form on a certain energy space. And this is of independent interest, that you can actually, turns out, look at parabolic equations. They will be sort of coercive on a certain energy space involving the half-time derivative. That was an insight that myself and Pascal Aucher and more research Egerts has been exploiting in our previous works. So what is this? You have L2, you introduce this inhomogeneous energy space, L2 normal V, and then you have sort of the square root of the heat operator, or what you would refer to as the first order Sobolev regularity in the parabolic sense, right? Which is grad X of V, and then you have this half-time derivative. This you sort of, if you have a second order operator in divergence form, this is natural, right? And then if you look at parabolic problem, at least from some heuristic perspective, it's natural to look at half-time derivatives. But the problem is just that in many cases, you don't really know how to get hold of this half-time derivative through your equation. And that's what I'm coming to. There is a trick to do that, actually. So what we then look at, we take a triple, we have this energy space with regularity, we have H, and then we have V prime will be its dual, the dual of this energy space. So we have this triple of spaces where this arrow means that the spaces are dense and continuously embedded in each other. So what we then look at is the operator is defined through a bilinear form, as stated. We split the half-time derivative into using the Fourier symbol. So this half-time derivative is given on the Fourier transform, so like the square root of the symbol, absolute value of the symbol. And then, of course, we get these sign things because we have the time derivative. So this is what is called the Hilbert transform. So you split the half-time derivative as stated, and then you look at this form here. So what is this form? This form is basically, if you look at the weak formulation for a parabolic equation as stated, what you then get is from the divergence. When you lift the divergence, you will get this term. And then if you split the half-time derivative, you see you can keep sort of this guy, say, on your u, and then you move over the other half-time derivative of v. So it's sort of a form that you get if you look at the weak formulation of parabolic equations, but splitting the half-time derivative. So what we then do is that this form, we let this form induce the operator h, going from the energy space to its dual through this formulation. We consider this as I said, as a bounded linear functional from v into v prime, defined as stated. So hu, that will create then a functional acting on v's in here, and the way it acts is given through this bilinear form. So that is usually the way, I mean, you induce operators from bilinear forms, right? In the sense stated. So as we then know, if you do operator theory contrast to PD, I'm more a PD person, you have to make sure that you have appropriate domain in which you work. So initially, of course, this operator H will be unbounded on the Hilbert space H, which was L2. So what we then do here, we consider a subspace, which is a space of all functions in the energy space such that this, when this HU act on it, is actually an element in L2. So this is this domain that we will consider the operator H living on. So this is, of course, an abstract, I mean, notion. So what is this, right? If U is in D, you might ask, I mean, what does it look like? So what happens is that you sort of, by making the statement, you're basically imposing implicit boundary conditions, some of at infinity, so that you can lift this guy here again, and you can lift this here, and what you get when this sort of act on U is an element in L2. So it pushes a lot of implicit conditions under the, well, it pushes some conditions on the behavior at infinite, at least, under the rug, and all this get abstractly embedded in this domain D. So what is then interesting here is you can actually start to do interesting thing with this operator H, defined through this bilinear form. And note now that, again, formally, this operator H coincides exactly with these unweighted parabolic operators I considered, which you see just by lifting formally the half-time derivative there and this guy over here. So formally, this H is equal to this sort of PD operator I was considering, right? But what is interesting here is that this form, as I said, a problem with a parabolic equation is to get hold of some coercivity so that you can do, for example, the Lax-Milgram theorem. For elliptic equation, Lax-Milgram is much relevant, right? Which means that the symbol of your form operator, you can estimate that below, say, with the L2 norm of the gradient. You use that all the time. You teach that in undergraduate courses or perhaps graduate courses for a way to solving linear equations, or say second order, also higher order, using functional analysis, right? Riesz representation formula. In the parabolic case, this is less clear because you have difficulties getting hold on coercivity in the time derivative. So this is a slide which is a really crucial in everything we have been doing since I started out here, is that there is a way, and this you could have some use of in other contexts. There is a way to make this bilinear form, sesquilinear form, actually coercive. And this is the trick. You look at the modified such form, where you see here that instead of just having V, you have 1 plus delta times the Hilbert transform, and then it acts on V. So if you look at this energy space I described, which is quite natural, but you have to get used to it, it turns out that this guy, 1 plus Hilbert roommate, it's invertible on that. It's a one-to-one map on that energy space for all deltas. So you can as well formulate your weak formulation of this operator equals, say, 0 using these particular test functions. So as it turns out that if you now look at the real part of this form and estimate it from below, which is, of course, you have all your estimate from above based on the fact on the boundedness of this guy. But if you want to estimate the some kind of coercivity of this, what do? Well, first of all, if you want to use the coercivity or accretivity of A that we assumed, then you get this, I think I call it C1, right? But then you also use the bound from above with C2 and then times delta. So you get from this term, you can bound that from below using this. And then of course here you see that this part, when the half-time derivative goes in here, it will integrate out the way it usually does in the parabolic case, which is your problem, right? But then you have this piece also. So you have half-time derivative delta ht here, and you have exactly there. So what you get is this. So now you see if you choose delta sufficient to small in terms of just the ellipticity of A, this will be a coercive form on this energy space. So this is something you can actually try to use also if you study higher order parabolic equations. What I mean higher order is that you have a higher order operator and then you add the time derivative, for example. You can probably then try to construct solutions in this appropriate energy space using this trick. And this is what now we call hidden coercivity in these operators. And originally I thought it was a completely new idea, which I had, but it turned out that you can also find it in a paper by Steve Hoffman and John Lewis a number of years ago. But in fact, it can be traced back to a paper by a man called Kaplan from 1957, where this observation was also done. But it's an observation which is worth being observed again because it has a lot of implications if you do parabolic equations. All of a sudden you can look at these equations the way you look at the elliptic equation, just have another energy space. So you can make it coercive on that. It's a big gain. So what then happens is that if you have this, then you can actually start to prove things of the following nature, namely that if you look at this operator H with this domain D, it turned out to be what is called maximal accretive, which means a number of things, but in particular, it means that these resolvents, if you look at sigma in the negative real on the half to the left in the complex plane, you have estimates on these resolvents as stated. And if you have that, it turns out that these operators, through a general theory about such accretive operators, you have a bounded H infinity calculus, and you can make sense of these powers using abstract functional analysis and functional calculus. In particular, you have, for example, this representation of the fractional powers of this H in terms of what is called the Balakrishnan representation, which sounds like a pretty Indian name, I would say. I have read these papers, very good papers from the 70s. Impressive work in general in the 70s by a lot of people doing functional analysis and operator theory. So in that way, you can introduce them. So let me, I'm running out of time. I'm talking too much. So let me then go to state a theorem, for example, what we are doing. So we say that now this u lambda is a solution to this equation. If it is the case that it has certain regularity in the lambda direction, which is nothing strange because the coefficient is not depending on lambda, and then that it satisfies this equation in this rather abstract setting, where this is given by the bilinear form we had before, and then this is the case. So it turns out that if this operator is maximal accretive, then another way to look at this is that minus H is maximal dissipative, and this minuses will generate what's called a strongly continuous semigroup of contraction. So, you know, you can get hold of a semigroup here in the same way as we discussed sort of an explicit semigroup in the case of the fractional heat operator. So what we then can prove, to give one result here, I probably would need another hour to do more, is that if you take an S and you define your u lambda as stated more or less as we had before, but now we have this rather abstract semigroup coming from the fact that it's maximal accretive H. And if you introduce u lambda as stated, then actually this u lambda will be a solution to the sort of PDE, if you might call it, or operator valued ODE. On the previous slide, we have some regularity estimates, which I'm not going to discuss here, but they actually turn out to be important. And here it enters the fact that we know that we work in this domain D, for which this is in L2. This is crucial for the argument. And also this extension has the property that this Dirichlet to Neumann map actually reconstructs these fractional powers of the operator. So to conclude here, since I'm running out of time with 1 minute, I think we started 2 minutes after schedule, right? Is that in this abstract setting, you can make sense of fractional powers. You can use a semigroup, but it's much weaker. And it is an open problem to see if you can somehow do a more slightly, perhaps more elaborate extension using some kind of semigroup and so for which you can have stronger estimates. And so far I have tried, but I have not been that successful. What you can do is you can connect then this extension operator u lambda here, this guy, to sort of a PDE problem to this kind of equation. And actually you can do what I discussed for the fractional heat operator and basically the Luis Caffarelli-Silvestri trick in this generality, at the price, to conclude, at the price that there is a lot of implicit information that you put into this assumption, that we all the time work with the function u in this domain D. But strictly speaking, what you would like to do is to work with just u's in the domain of HS. But then you have to be able to construct an extension based on that assumption. At this point in time, that seems to me like an open problem. So our results, I think, are interesting, but there is a lot of implicit information hidden in our assumptions, which is perhaps not that easy to penetrate and digest. So of course I have much more material, but I think I should stay within the time frames, and thank you for listening to this. I just want to give you the last slide where you can read some of these things. You can send me an email or interested. The first paper is on archive. Then something about weighted operators in preparation. Then something related to this, which I've done recently, is you can look at some kind of tug of war games in this setting. I think that's a lot of interesting open problems there. And here are the original paper on the Kato, one by me and one then with Pascal Auxerre and Maurice Eggerts and myself, where we actually solved this Kato problem for these parabolic operators unweighted. And I think the techniques in this can be used for a lot of interesting problems in analysis. And in particular, you should read up if you're interested on this idea with the hidden coercivity, because it's a nice little trick which gets everything going. So thank you.
Thank you very much for this wonderful talk. Maybe we should unmute ourselves and thank the speaker. Now I open the floor for questions.
It's kind of a lot of, I was probably going, I don't know if I'm going too fast or too slowly, but there is a lot of things, and it becomes rather abstract, of course, if you go to complex coefficients, and most people are not used to it. But it is it's a strong it's a strong tool once you're in there and being able to do estimates for that, because as you know, all this operator theory tend to be done in the complex plane, and if you want to do a certain boundary value problem, you want to do use the strength of complex analysis to study how your operators as analytic functions and so forth. So it is indeed you're going up one level of abstraction, but once you're there, you get much more freedom to attack certain problems. So, but I guess in general, if you're undergraduate or graduate student, you tend to, if you're not an expert, you tend not to work with complex coefficients. So that's something to get used to.
So Nyström, one question.
Yeah, here we go. Yeah.
So you have the solution to the Kato square root problem with the kind of assumptions that you listed for the coefficients.
Yep.
So can you just go over your last slide, because I'm a bit confused. So why then the two domains have to be different? Because you have been able to identify that the spaces are the same at half, and then you have.
So what slide was that? Was this stuff?
Yeah, the domain of H's. So I got a bit.
You mean this, right?
Mm-hmm, mm-hmm.
Yeah.
Yes.
Yeah, I mean, the thing here is that I started out with this domain, right? Which I called big D, and that was sort of the domain for which I introduced this operator H. And then you, of course, would like to introduce, you can introduce fractional powers, and somehow these domains for this operator is basically these functions U, right? So what we have been doing here is that we have worked, these domains get nested as stated, right? The larger S, the smaller space. So what you would like to do is you would like to start with a function U in, say, this space, and do some kind of extension, then prove that the Dirichlet normal map give you fractional powers. The question is how you do that. This space D that we have done this for is what is called a core. So it is in all these spaces. It contains the most information, but it's also dense in all these spaces. But of course, these spaces can be larger. But our problem here is that we use rather basic, if I may say so, or rather established semigroup theory, which basically demands that you have to work with functions which is in the domain of H, not in the domain of HS.
Oh,
so
okay.
It's an open problem how to construct this extension, just assuming that the U is in the domain of HS. That's what I meant.
I see.
Mm-hmm. And it's, I don't know, one thing to look at, which I actually look quite a lot at, is there is this paper of, well, there are a number of people who worked on this, of course, in this more abstract operator theoretical context, by Wolfgang Arendt and Tom van ter Elst, I think his name is, where they do this kind of things where you take the stationary operator, and you look at the Dirichlet normal map and appropriate spaces and this kind of stuff. And then they can do a lot. And why can they do that? Because if you take the stationary version of our operator, then E to the operator, E to the lambda, the operator, is what is called an analytic semigroup, because of the assumption on the ellipticity of operator. So in the elliptic case, the theory of semigroups, you get a lot of things for free. It's just the heat semigroup with all the good properties you can think of. In this case, when we have now we would like, strictly speaking, then to take a semigroup which look like E to the minus lambda, and then something which relates to this parabolic operator. And then it is because what we only know a priori is that this is maximal accretive, which means that the spectrum is all of the right part of the complex plane, we don't have any good estimates on such a semigroup, if we could even define it. So I tried several things, to try to do what Arendt and the others did in the parabolic, using this idea with hidden coercivity and so forth. But frankly, so far I didn't get it. I didn't get it to work out. But if you're interested and would like to look into that, I think it's a good idea to read the paper of Arendt, read our paper, and then think about how can you make use of this idea of hidden coercivity, perhaps to do even more refined extension operators beyond using this semigroup that we use in this paper, or this paper I mentioned at the end. There in this paper we use this rather rudimentary semigroup or extension. Yes.
Okay. And now it's clear.
Okay, great. That's good.
So hello, thank you, Nyström, for a very nice talk. So I just
thank you.
Add one remark. So I'm a probability theorist, and
okay.
So even though I don't know much of this PDE side, but I just want to make one remark that usually this kind of technique of like abstract construction, this also is in the probability theory literature. So when people want to construct some very, very wild Markov processes, they use these kind of Dirichlet form technique. So some names are Fukushima and co-authors. They also use these kind of techniques to construct such processes. So yeah, it's very related to that.
That's interesting. No, I mean, I agree. I mean, this if you have this form, you can look at it from a lot of perspectives. And as I said, I think in the beginning, it would be great if one were able to have the knowledge both of people doing probability and analysis. There's a lot of interesting connection you can make. And some people have been, of course, able to do that, but probably too few of them. And it's what you say is rather interesting. I haven't seen, suppose you use this parabolic coercive form that I mentioned. The question is, I don't think perhaps one can look at that from a somehow Dirichlet form perspective in probability also. I don't know. I of course I know that your Dirichlet forms and this kind of stuff, right, in the elliptic case, but perhaps there is interest to look at if one can make something with this. Let's see, where did I have it now? The hidden coercivity stuff, right? Oh, sorry about this, many slides. This thing, perhaps one can, I don't know if one can make anything out of this coercive form in probability. You seem to indicating that, but at least you're saying that it's Dirichlet forms are relevant, right? Perhaps there is something you can connect to probability in this with this parabolic sesquilinear form also. I don't know.
Yeah, maybe.
Yeah, it's interesting anyway. Thanks for the comment.
Yeah, sure. Thank you.
So another elementary question. So if we instead look at the symmetric case, real coefficients, so do we have the Littman-Stampakia-Weinberger type estimate for the semigroup for the fractional powers?
Yeah, I guess we have, right? Because in that case, that's a good point. I didn't say that, right? Let's see. If you localize, right, the point is that yeah, let's skip. If you localize this, yeah, already in the real case, of course you get the weighted operator, right? And you're asking, I mean, do you have local regularity for those? That's what I think they're asking you. Yeah, and that was done, you know, this paper I mentioned by Koenig, Fabes and others, the elliptic part, there was an Italian mathematician, Filippo Chiarenza, who actually wrote a few with other colleagues doing the parabolic version of those papers. He didn't reach as far, and this didn't do it as, you know, in all aspects, but he proved basically local regularity for the weighted versions of these operators, where you place this with a second operator in divergence form with, say, time independent but real coefficients. And if you have an A2 weight, he proved the Harnack inequality and the Hölder continuity estimate for weak solutions and so forth. So if that is what you're asking me, that's true, and that's something we use in the end here, where we do the localization. And then I didn't really, of course, get to that. We prove these kind of estimates, right, for this fractional operator in the case of real symmetric. That actually don't have to be symmetric with real coefficients. And actually, these are derived after localization by the corresponding result by Mr. Filippo Carenza and so forth. And again, these results are basically also derived if you have time-dependent coefficients. You do exactly the same way as you do if you don't have a weight, because in this case, I mean, the operator or the equation is homogeneous in the weight, so you use the same parabolic cylinders and all that stuff. So as you can do Moser iteration, or basically what is the Georgi estimates, in the same way as you do in the unweighted case. But in the literature, it's done in the 90s by Carenza and co-authors. If you look at some of our papers, I think at least this paper of Malta, there are references to at least a couple of papers there. Did I answer your question, or did I talk about something else?
No, I think it's kind of clear now that I think about it, in the sense that over here, if I look at the non-local operator and if it equals the Dirac, that would reflect at the level of the extension problem on the weighted Neumann derivative. And then what I can do probably is that I can still evenly reflect, and then I get that it solves in the extended space 2 times the Dirac on the right hand side, and probably one can run through the same local theory.
Yeah, that's basically what we do, right? It's just that we are slightly more well, I wouldn't say more careful, but I mean we have this slightly more abstract operator to start with, right? So what we do get is that we initially get the solution to this. We do exactly what you say, right? Flip it over, we get the solution, and we get the solution to this equation. But now we got what we call the reinforced weak solution, which is stronger form weak solution, because it's a solution which you do not only control u tilde and u, the gradient, spatial gradient u in L2, but you also control this half-time derivative. But of course, it will be if it's reinforced, it is also a weak solution. So you can go to it's a weak solution in the standard form, and then you can use local regularity for these operators in the case of real coefficients to make conclusions. So I think you're basically summarizing what I'm saying.
Except that over here, the Neumann derivative would not be 0, but it would still be like the Dirac measure. But we still have the leverage of evenly reflecting, and then we get twice the measure for the.
Well, this is derived. You know, this is if I flip it over and to actually get that the thing I flip over is a solution over the boundary. I use that. Are you assuming that this Dirichlet to Neumann map is equal to 0, right?
Yeah. But even if it is not, then even if we flip, then we still get twice the measure. So I guess still one can apply the local theory for fundamental solution, I guess. So I was just wondering that if you have the fundamental solution instead, where the Neumann derivative for the extended one is not 0, but the Dirac mass. But then if I flip it over, it becomes twice the Dirac mass. And then one can more or less, but because since you have the Harnack inequality for this, one can more or less imitate the Littmann-Stampakia, Weinberger, or the Aronson-Serine kind of argument to get the. So that is what I was kind of.
Yeah, that's. I agree on that. I agree on that. At least if you have. Yeah, I agree on that. And that's basically, I mean, what we're doing. There is some issues after all. I mean, in the sense, the way. Yeah, well, let us say I think I agree with you. Sort of, I'm not completely sure, but probably you're saying something that is in line with what I'm thinking and what I'm saying. So thanks for the comments.
But for the non-symmetric case that you're describing, nothing is known about the semigroup. Is that correct?
No, I mean then it's much less clear, right? That's I don't know if you're thinking about it from a note that I say we have time-dependent coefficient here, right?
Mm-hmm.
So are you talking about that? That's a key difficulty, right? Are you talking about the time-independent case or the time-dependent case?
Time-dependent case.
Time-dependent case, yeah. Maybe you can do it in other ways. I don't know. So how do you define the semigroup in the time-dependent case?
Mm.
That's not really completely clear to me, at least, unless you do it somehow the way we do it. But, in the time-independent case, it's straightforward, right? You do it more or less exactly like in the heat case. Yeah. No, but it's good that you're interested. I think there's a lot of things to look at, and then of course I know you know this stuff. I mean, you worked a lot about it in the thin obstacle problem and so forth, right? So you are well aware of the things to think about.
Well, not much on the functional analytic aspects that you described today. So all of it was kind of new for me.
Oh, okay. Oh, that's good to hear. Yeah.
All right. Yeah. Thanks again.
Oh, thank you.
Are there further comments from the audience or questions? Very well, then let's thank the speaker again.
Oh, thank you.
Thank you very much.
Yes.